Address resolution is the glue between network layer addressing and link layer forwarding. When a host has an IP address to reach, the packets are addressed at layer 3, but to actually deliver those packets on a local network, the sender needs a link layer address. Address resolution is the process that discovers that link layer identifier so frames can be delivered on the same network segment. At its core, address resolution answers a practical question. Given an IP destination that is known or routable, what MAC address should I put in the Ethernet frame so the local switch or NIC can forward the packet to the correct device? The need arises because different layers use different naming schemes. IP identifies logical endpoints, while MAC identifies physical interfaces on a local link. Without a mapping between the two, the network cannot bridge the gap from logical routing to physical delivery. How does it work in practice? On IPv4 networks, the Address Resolution Protocol, ARP, is the standard mechanism. When a host wants to send an IP packet to an address on the same subnet and lacks a MAC mapping, it broadcasts an ARP request, asking, "Who has IP X? Tell me your MAC." The owner of that IP replies with an RP response that contains its MAC address. The requester stores this mapping in its RP cache and uses the MAC to encapsulate subsequent frames. For IPv6, the Neighbor Discovery Protocol, NDP, serves the same purpose using multicast rather than broadcast. Nodes send neighbor solicitation messages and receive neighbor advertisements with the resolved link layer address. Both ARP and NDP rely on the broadcast or multicast domain and are scoped to a local network segment. There are practical details worth knowing. Address resolution uses caches to avoid repeated broadcasts. Systems keep an RP or neighbor cache entry with a timeout. Gratuitous RP or unsolicited neighbor advertisements let hosts announce their mapping proactively, useful for failover and updating switches' MAC tables. Proxy RP and proxy NDP allow routers or gateways to answer resolution requests on behalf of remote hosts, enabling certain legacy topologies or NAT scenarios. Conversely, address resolution is limited to the broadcast or multicast domain. If the destination is on another subnet, the sender resolves the MAC of the gateway next hop instead of the final host. Why does address resolution matter? First, it is essential for reachability on Ethernet and similar links. Without it, IP routing cannot be translated into actual frame forwarding. Second, address resolution affects performance. Broadcasts and multicasts used for discovery consume bandwidth and CPU, and cache misses cause additional latency for the first packet. Third, address resolution is a frequent source of operational issues. Stale cache entries, incorrect proxy RP configurations, or misbehaving devices can cause misdelivery or intermittent connectivity. Finally, security depends on reliable mappings. If an attacker can poison caches or spoof replies, traffic can be hijacked or disrupted. What are the key features and trade-offs of address resolution? Caching is central. Caches reduce discovery overhead, but introduce freshness and consistency concerns. Timeouts balance churn and responsiveness. Short timeouts mean more discovery traffic. Long timeouts increase the window for stale mappings. Broadcast-based discovery is simple and widely compatible but does not scale well in very large Layer 2 domains. Multicast-based discovery, IPv6, reduces broadcast storm risk but still depends on local reachability. Proxying and overlays offer flexibility but add complexity and potential opacity in troubleshooting. What are the implications for network behavior and operations? Frequent ARP or NDP traffic can indicate misconfiguration, ARP storms, or many new devices joining the network. It can also exacerbate congestion in dense environments. Stale RP entries cause packet drops or delivery to the wrong interface until caches refresh. ARP spoofing, or NDP spoofing, neighbor cache poisoning, can create man-in-the-middle or denial-of-service attacks. Mitigation techniques include dynamic ARP inspection, DHCP snooping, RA-ND inspection, and cryptographic protections where available. In trusted and cloud environments, address resolution interacts with overlays and virtual switches. Tenants may have isolated address spaces and controllers that manage mapping centrally, changing the troubleshooting model. Operational best practices help monitor RP and neighbor caches, use appropriate cache timeouts for your environment, avoid unnecessarily large Layer 2 domains. Document proxy RP uses and enable sanity checks like gratuitous RP handling and RP inspection on access switches. Where security is a concern, use authentication and control plane protections, and consider moving sensitive services behind proxies or gateways that restrict direct host-to-host discovery. Address resolution is a small, simple mechanism with outsized influence. It converts logical destinations into physical delivery instructions, and it does so continuously on every local network. When it works, traffic flows transparently. When it fails, devices cannot find each other, performance degrades, and security holes appear. Understanding ARP, NDP, caches, and proxy behaviors gives you immediate leverage in diagnosing local connectivity problems and in designing networks that are both efficient and secure. That is address resolution.